Okay, so today in class we talked about how to find the area underneath a curve. So if the function is real simple, like a straight line, we can just use our basic geometry facts to find the area. But if the area is a curve, then our basic geometry kind of falls apart on us. So what we're going to be doing is taking some notes on how to find the area under a curve. But before we do that, I do want to mention that there are two types of integrals. One type is for finding the area under a curve, and that's called the definite integral. And then there's the type of integral that we use when we know the first derivative and we're trying to find the original function, and that's called the indefinite integral. Okay, so I'm going to write these down for you. So the indefinite integral is when you know the derivative and you're trying to find the original function. So the indefinite integral is what we were practicing last week. So when you have your integration sign and you say x squared dx, for example, you would take the antiderivative of that. The antiderivative is 1/3 x cubed, and then you add a constant. This is the indefinite integral. So notice I don't have any numbers that I'm going to evaluate it on. So this would be, what I've got going on here is basically I know the derivative. Oops, where's my ink? I've got 20,000 red pens and I pick up one that's not going to work. There we go. So this part would be our derivative. And then what do we get out of this? We get the original function. Okay, so that's the indefinite integral. So when you know the first derivative and you're trying to find the original function. And that's when we have this constant of integration that we got to put on there, because if we were to take the original function and take the derivative, if there is just a number over here, when we take the derivative, it disappears. So we don't know what it is. Okay, when we want to find the area under the curve, we don't actually care about what exactly was the original function. We don't care about that because that's not what's happening here. When we have the area under the curve, we have the function that we want to find the area underneath, and we're just trying to figure out what the area is. We're trying to figure out what is the sum of all the rectangles that get put together to get the area. So that's called the definite integral. So we use this to find area under a curve. And there's a few other applications of it, but that's kind of the generic way of talking about it, to find the area under a curve. So when we have the definite integral, we're going to actually get down to a single number answer on that. Okay, so an example of this would be I can use the same function, x squared dx, and then like we did in class today, I want to evaluate it from one value of x to another value of x. So in class today, we were looking at y equals x squared, and we were evaluating it from 1 to 4 along the x-axis. So this is what a definite integral looks like when you have the numbers here, because it's telling you that you're actually going to evaluate it and you're going to find the actual area. Okay, so when we do that then, we take the antiderivative just like we did here. So we'd have 1/3 x cubed. But instead of writing plus c, we don't care about that because this isn't really a derivative, and this is the original function. This is actually our function. We're just trying to find the area underneath it. Okay, so it's a little bit different thing that's happening. So what we do, next step, is we put that in brackets, and we say we're going to evaluate this from 1 up to 4. And then what we do is we can just substitute this in, find the value, and then substitute in the 1, find the value, and subtract them. Okay, so if I were to finish off this problem, this would give me 1/3 times 4 cubed minus 1/3 times 1 cubed. And we can finish that off, and we get 64/3 minus 1/3, which would give us an answer of 63/3, which equals 21. So that's what we did in class today. We did the definite integral, which finds you the area underneath a curve. Okay, so the indefinite integral, we use it when we know the derivative of a function and we're trying to figure out what was the original function. We use the definite integral when we would just want to find the area underneath that particular curve that we were given. So we're given this curve, we want to find the area underneath it. That's when we use the definite integral. Okay, so there's something called the fundamental theorem of fundamental theorem of calculus, and it's basically what I just did here. So I'm going to write down a little bit of things. Okay, first of all, let's get a little more precise about the definite integral. Let's talk about the parts of the definite integral. Okay, so this was an example. So this was an example of the indefinite, and this is an example of the definite. So let's look at the parts of the integral. So if I'm looking at my definite integral, I have the summation notation, and then I have my starting and my ending points, and then I have f of x, my function, and then dx. So what did this mean today? What did this mean? What did we figure out in class today? This symbol right here means sum. So we're going to add all the rectangles, and then this was the height of the rectangles. So this was the height, and then the dx, this was the width. That was the width of each of the rectangles. And then this is our starting x value, so where we're starting on the x-axis. Starting x value. And this is our ending x value. Okay, so, and then what were we doing with this? This was the sum of all the rectangles with a height of f of x and a width of d of x to get the area under the curve. Okay, so we're going to write that down. This is what this is talking about. This is the sum of all the rectangles with a height of f of x and a width of d of x. And we talked about d of x is going to 0. We want as many rectangles as we can, so we make the width smaller and smaller and smaller, so it's basically like a limit to get the area under the curve. Okay, so the process that we use, that we did up here, is called the fundamental theorem of calculus. So we're just going to write that down so that if anybody ever says to you, oh, do you know the fundamental theorem of calculus? Yeah, you do know the fundamental theorem of calculus. Okay, so we're going to write that down. The fundamental, it sounds so important, fundamental theorem of calculus. Fundamental theorem of calculus. So if I've got the sum from some x value a to some x value b of f of x dx, I can find that value or that area under the curve by taking the antiderivative and evaluating it at b, and then taking that antiderivative and evaluating it at a. Okay, so remember that capital letter F, this is the antiderivative. Antiderivative. Okay, and so B, the B is where it ends, and the A is where it starts. Okay, ending X x value, and the a is the starting x value. And that is the fundamental theorem of calculus. And we already have an example of using the fundamental theorem of calculus over here when we did the one from class today. Okay? So now you're going to go practice this in Math Space. Okay? A couple things, though, that I want to write down because we're going to work on these in class. There are a couple other basic rules of integration. So these are in your formula packet. But no, you know what? I changed my mind. We'll just paste those in later. I was going to give you some more basic rules, but we won't worry about that right now. Okay, time to go to Math Space. And we're going to practice the definite integral.